Well, hello all. And this is our first Google Meet, or the future of education. With the pandemic, we can't all go and play outside in the pandemic. So the secret is we're all going to have to meet virtually on Google Meet, Zoom, something like that. So people are going to be at home, and then we're going to all meet together and learn. And you know what? Like Little House on the Prairie, I think it was, where you have these little farmhouses and farm schools. Why shouldn't grade 10, 11, and 12s meet together on the same virtual classroom, Google Classroom? They all do electricity, and today we are going to be doing electric circuits. So let's do some electric circuits. Now, for some reason, students do electricity in grade 8, grade 9, grade 10, grade 11, and grade 12, and they arrive in grade 12 and they still can do nothing. Is it the teachers? Is it the method? Why is it that the same stuff is scheduled in the syllabus for grade 8, 9, 10, 11, and 12? Do they expect you not to be able to learn anything in 8, 9, 10, 11, and then hope you're going to learn something in grade 12? What is wrong with the system that nobody can do electricity? Now, electricity is such an important part of our lives. We we are a generation that could almost be characterized by the electronic generation. We're always on our cell phones. That's electricity. We're on our computers. We're on our TV. Everything's electricity, electricity, electricity. And yet nobody knows a thing about electricity. You give people simple problems and they are absolutely stumped. Now, my feeling is that there are a lot of little rules to electricity and electric circuits. And unless you have sat down and learned those rules, unless you've somehow internalized and made sense of them, you're not going to do well. Okay, so let's just have a look at a circuit. Well, let me just go back there to the circuit. Let's present now your entire screen. Okay, let's present and allow our entire screen to be presented. And we're about to present our screen. I'm very interested in trying this. So you are presenting and presenting to everyone. Okay, how come I can't see my screen? So let's go to there. You're presenting to everyone, and I'm hoping, look, we're trying this out. I'm hoping that whatever is on the screen you guys can see. Now, there seems to be two people. Someone else has joined us, and I hope they can see us. And I hope I don't have to let them in or anything. As I say, we're trying to figure this out as we go along. Okay. So these are from past matric papers, and here is a typical electric circuit. Now, normally by grade 10, everyone is aware that that is a cell. And normally they know that the long arm is the positive side. So I remember it by, if you take the long arm and you divide it into two little shorter bits, you cut it in half. The long one becomes the positive and the short one looks like a negative. So that side's positive and that side's negative. Okay, and then I don't know if everyone knows we use conventional current, meaning current that goes from positive to negative. So that's another rule that people have to know. And actually, to solve this problem, you've actually got to know so many of the rules. For example, what are these little square things? Well, they are, I'm sure most people know that that is a resistor, 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 resistor. So there's four of them. The four resistors, P, Q, R, and T, in the circuit below are identical. The cell has an EMF and negligible internal resistance. The switch is initially closed. Now, I hope everyone can see that that is a switch S, and it is closed. Now, what one also has to know is the difference between series and parallel. Parallel means the current has a choice where it can go. So if the current leaves the positive terminal, And the positive terminal can have any voltage. But now if I had to ask learners, what is meant by voltage? Most people, what is voltage? Oh, we've done this for 5 years, but what is voltage? I have no clue what voltage is. Okay, think of it like this. This is home. Your mother packs you a lunch and sends you out full of energy. The amount of energy you leave the positive side with is your voltage, the energy per charge that leaves here. And the rule is you've got to come back at the end of the day or the end of the circuit with, you've got to come back with zero energy. So on the negative side, the energy is always a big fat zero. I don't know. That's filling it in with yellow. Okay, well, we're playing around here. But let's say this side, normally batteries can have, or cells are 1.5 volts, whatever. Makes no difference for this problem. What is important is you know that series means the current that leaves here first goes through this, then goes through these two, then comes through here, then comes back. There's no other choice. The only time there is a choice is here. There's a choice. Okay, great. Let's get rid of that. I wonder how we can have a full color of zero. I guess there would be a transparent somewhere around here. I'm not sure how we do that. Let's just try that. Okay. Yeah, but it still wants to fill it. Okay, well. So what you've got to know is that when you have something in parallel, there comes your current. Let's get a better color here again. Let's go back to blue. Your current now has a choice. It can go here, or it can go here. And that means it's in parallel. And now the current flows parallel to each other. And then it comes together again, and now we're back to a series circuit. Okay, so it goes, everything here is in series. That resistor's in series because there's nowhere else for it to go. Then when it comes to a split, the current has got a choice. So now when it has a choice, we say it's in parallel because the current is flowing in two little rivers parallel to each other, and then the two rivers come together, and now we're back to the same current. So people have to know the rule that the current everywhere in a series circuit is the same, and then the current in a parallel circuit splits into the two little rivers, or we could have had a third little river here, and we could have had 3 resistors in parallel. And then the current would have a choice of going this branch, or this branch. But if you add the current in this branch and this branch, it must add up to the main current, because the main current splits. It's like the river. The water's got nowhere to go. Okay, so what is voltage? It's basically your mother or home is packing you when you leave with a certain amount of energy. Now, during the course of your day or your circuit, you're going to drop energy. And where do you drop energy? And you're going to come home. The rule is you've got to come home with no energy. So if you start with 5 volts of energy, you've got to come home with 0 volts of energy. Always on the negative, it's 0 volts of energy. You come back with nothing left. Okay, so how do the charges decide where they're going to drop the energy? And here we come to our main stars of the show. The main stars of the show are our resistors. Okay, so they are our resistors. They are the main stars of the show because they are the guys that are going to give off energy. And so that's going to give off energy. And that's going to give off energy. And that resistor is going to give off energy. And this resistor is going to give off energy. Okay, so the energy has got the electron, or if we use conventional current, the positive charge is going to come here, and it's going to lose some energy there. The charge is going to half, some is going to go through here and some is going to go through here. So now we need a rule to decide on where does the current, how does the current get divided? If you're going to divide the current, how do you divide it for resistors in parallel? Well, if they're identical resistors, then you're going to get an identical current. So this current here plus that current is going to be, those two are going to add up to the main current. So each of these is going to have half the current of the main current. Now, if that was a bigger resistor and that was a smaller resistor, resistors resist current. That's a rule. So the current always chooses the path of least resistance. So if that's a bigger resistance, more current will go through the smaller resistor. If this is the smaller resistance, more current will go through the smaller resistor and avoid the big resistor. So that is a rule. But if they're identical, you're going to know that each is going to get exactly half the amount of current. So to do this kind of problem, which asks you when the switch is opened, what happens to the current? You see, this whole question is when switch is now open, which one of the following combinations of changes will occur in P, R, and T? Now, this is a metric problem, but I think that most of our grade 10s, if they learn the rules, could just as easily learn how to do a metric problem. Okay, so one of the rules for solving this kind of problem is just, first of all, combine all resistors in parallel into one equivalent or equal resistance. Those two can be equal to one resistance. And how do we do it? Well, we have a rule. We have a formula for, here's our text. Let's just move our text box to here. We have a formula that is 1 upon R parallel equals 1 divided by R1 plus 1 divided by R2, etc. Okay, so that is how we work them out if they're in parallel. So that is our formula for resistors in parallel. So what I always say is just if each resistor is the same, let's give them an arbitrary value of 1. Okay, so let's now find out what the combined resistance of these would be if they were each 1 ohm. So we say 1 divided by R parallel is going to be equal to 1 divided by 1 plus 1 divided by 1. And you know that 1 divided by 1 is 1, and 1 is equal to, so the total is going to be equal to 2. But we've got to invert it, because we don't want 1 upon R parallel, we want R parallel. So we've got to put 1 divided by this answer here. So that is going to be 1 divided by 2 is going to be equal to a half. So we can now say the equivalent or combination of those two resistors is going to be equal to, okay, let's just write it again. Here's our text box. Let's say, therefore, R parallel is equal to 1 divided by 2. To invert this answer, we have to put 1 upon whatever that is to get the inverse. And so we're turning 1 upon R parallel upside down, and it becomes R parallel upon 1 is equal to 1 upon 2, and which is going to be half an ohm. Okay, so there we go. We now know that the resistance of the two together is half an ohm. That's 1 ohm. That's 1 ohm. So what again do I say? We have a rule for this we can now regard as just one resistor. So if that's 1 ohm, that's 1 ohm, and that's half an ohm, we have a formula for resistors in series. Because now the current has got nowhere to go. It's got to go 1 ohm. This we know, we can regard it as one resistor, one equivalent resistor of half an ohm. So it's got 1 ohm, then it goes through the half ohm in series, and then it goes through this 1 ohm. So we can write that our resistance in series is equal to R1 plus R2 plus R3. We've got 1, 2, 3 resistors, which is going to be equal to 1, I don't want to leave the space, 1 plus a half, which is 0.5, plus 1, and that's going to be equal to 2.5. So that is going to be our total resistance. We could say R resistors in series, or we could say R total. Okay, so 1 plus 1 is 2.5, 2.5 ohms is our total resistance for the whole circuit, because now those have been combined into one resistance in series with those and those. Now there's another rule that we're going to apply, which is Ohm's rule. And Ohm's rule, it goes something like this. Let's just move this text box here. That amps equals V divided by R. Okay, so that is Ohm's rule. It comes in various variations. You could say volts is equal to amps times resistance, or resistance is volts upon amps. But you've got to know Ohm's law. But because we're trying to find amps, we're going to use the formula amps equals V upon R. Now, here's another rule that we're going to use. We could say amps total equals volts total over resistance total. So we could apply Ohm's law for the whole circuit, or we can apply Ohm's law for just one resistor. But why don't we apply it for the whole circuit? Okay, and that's going to be equal to, now we're not given a total voltage or EMF here. So why don't we just make this a nice big fat 1 volt? Okay, just choose an easy number, because we're going to then do a second circuit. Okay, so we know, just you choose a number, because we're going to, whenever you have two circuits to compare, because we're going to compare it now when the switch is open. So what is the total voltage? We've just said let it be equal to, let it be equal to one, whoops, let's just say that again. Okay, I total equals V total divided by R total equals, so what is the volts total? We said let it be 1 divided by, what was the total resistance? It was 2.5. And reaching for our calculator, it's 1 upon 2.5. 1 divided by 2.5 equals 0.4 amps. 0.4 amps. And there is going to be the current that flows through this whole circuit. Okay, did you see what we did? We said apply Ohm's law to the whole circuit. Now I know that the current is 0.4 amps. It flows through here. 0.4 amps goes through here, but now it's got a split. So I know 0.2 amps goes there, and half of it, 0.2 amps goes there. Then it recombines back into 0.4 amps, and 0.4 amps flows through this. Okay, so what do we do when we have a problem like this? Just give each resistor an arbitrary easy number like 1, give the cell an easy number like 1, and use Ohm's law and your formulae for resistance to work out what the current would be. Okay, so now we know that the current through each of those is 0.2, and the current through each of those is 0.4. Now, what happens when that switch opens? It means, and there's a rule, when this is an open circuit, you can actually ignore all of the part that's in the open circuit. That means you can ignore resistor Q completely. And so now we're left with just 3 resistors in the circuit, P, R, and T. And now why don't we go through exactly the same process and work out what is the total resistance and then the total current for the new circuit, which is with this circuit open, switch S is open. Okay, so let's work out the total resistance now when this switch is open, and we can ignore Q. No current can flow through Q anymore. And so let's use a text box here. Let's drag it to there. We can say now we've got 3 resistors in series. So we could say R series in our second case equals P, which is equals R1, 1. I'm just taking a shortcut, plus 1 equals 3 ohms. You see how the resistance has actually gone up. It's gone up from 2.5 to 3 ohms. And so let's work out the current through our new circuit when that switch is open. So we're again going to apply Ohm's law. Let's get a text box. Let's drag it here. For amps, I equals V divided by R equals, the voltage hasn't changed, it's still 1, equals 1 divided by 3, which is, I don't even need a calculator, 0.33 amps. Okay, so you can see that our amps has gone from, in the first case, it was, our amps were 0.4 to 0.3. And there's nothing to divide it. So this one's getting 0.33, this is 0.33, and this is 0.33. And now we're able to compare the case with the switch open and the switch closed. Okay, so when the switch is now open, which one of the following combinations of changes will occur in P, R, and T? Do you see how they leave out Q because they know Q is not in play anymore? So what are we looking for? We're looking for a increase of current. Look, the current through R was half of 4, which is 0.2. So it's now the current in R has increased. So it's one of these two answers. Current in R has increased. It's gone from half of 0.4, which is 0.2. It's gone from 0.2 to 0.3. And these ones have gone from 0.4 to 0.3. So R has increased and these ones have decreased. Increased, decreased, decreased. So this one has, R has gone higher and T and P have gone, their current has decreased. They've gone from 0.4 to 0.33. So the answer must be D. Here we go. So we've solved that problem. Okay, so let's stop. Let's go back and go stop presenting. So let's go to stop presenting. And I don't see anybody here yet. Although I know people are wanting to join our chat, but just wondering how we can let you in. I don't see anyone asking to come here. People. I just see one person. I don't see any other people in Google Meet. So we're going to have to go back and just carry on with presenting. My apologies if I've locked anybody out. Google. But anyway, this is all new. And yeah, it should ask to add people. See, add people. Nope. I don't see anybody waiting to come on. But, okay, let's go to carry on presenting. Let's present our entire screen. And okay, so we're going to show you the rules for doing electricity. Okay, it says I'm presenting to everybody. So I'm going to go to notes and let's have a look at this, the rules regarding circuits. Okay, voltage is the energy difference a charge possesses between 2 points. Got to learn that. Voltage only changes when it hits a resistor or a cell. Energy is lost across a resistance. Remember we said that the resistors are where the little charges are sent off by mommy from home. That's the battery or the cell. And only when they encounter a resistance do they start to give away some of their resistance. The current through every component in series is the same. Remember that we just did that in our problem. Now it says color a conductor with a color until it hits a resistor. That's to show that it has the same voltage. Very good practice that. Let me show you what I mean by that. Okay, so let me show you what I mean by that. Choose a color. Okay, let's choose a color. I'm colorblind, but let's choose that color. So choose a color, and that represents a voltage. Now, when it hits a resistance, it will change color. That means change voltage. Okay, so let's choose one of these septic. Okay, let's choose a different color for this. Let's choose a blue for this. Okay, come on, stop it. I want to draw something here. That's supposed to be in a different color. So that, wherever you have a different color, that means a different voltage. Okay, so the voltage, let's say this is 1 volt here when it leaves the battery. By the time it's got through a resistance, it's changed to a different color. Then here would be another voltage. You see all the conductors, and let's give that a different color. Let's say it's that color. And then this here would be another color, which would be a different voltage again. That would all be 0 volts. So let's change that to a different color. This is a very good practice to get into. Okay, so this color represents everything that's 1 volt. This color represents everything that's 0 volts. And these are different voltages. It's good to know that your voltage has changed after each resistor, but that everywhere on here is the same voltage. Okay, so that is our principle there. I just want to go to my rules. Sorry, where did I put them in? Preview? No, not in preview, in notes. Okay, there's our rules. The current through every component in series is the same. Color conductor with a color, I showed you how to do that. Current is how many charges pass a point in a second, not how fast they flow. Voltmeters have infinite resistance and do not carry current. Okay, so voltmeters you must think of as having an infinite resistance. Voltmeters are connected in parallel. This is a rule. Ammeters have negligible resistance and carry all current. Whatever, they just like have zero current, a zero resistance. Therefore, the whole current goes through it without changing. Ammeters are connected in series, meaning you have to break open the circuit to insert an ammeter. When connected properly, meters do not change the circuit, and so they can be ignored. So in the exam, when you get circuits with ammeters and voltmeters, you can simplify it by just ignoring them. Ohm's law states that for any resistor, the greater the voltage, the greater the current, or I is directly proportional to V. Here we've used Ohm's law, V equals I upon R, to solve that problem. Cells in series increase voltage. So if you have more cells in series, they increase the voltage. You just add the voltage of each cell. Cells in parallel do not increase or change the voltage. Here's the formula for resistors in series. We use this for resistors in parallel. Now, here's something that most students don't realize. Resistors are conductors too. People always think that resistors resist current. No, resistors carry a current. They sometimes increase the resistance when they're in series, but they sometimes reduce the resistance when they're in parallel. Resistors can reduce the total resistance. Resistors can decrease resistance in parallel. You must remember that rule, because learners tend to think that resistors only increase resistance. They do that in series, but in parallel, they reduce it. Resistors decrease resistance compared to air. Air doesn't conduct, but if you add a resistor, it will conduct. So obviously the resistor's got less resistance than the air. Resistors in series just add their resistances. Most problems involve finding an equivalent or combined resistance. That's what we did with that problem. We combined the two in parallel, and then we combined all three resistors to get our total voltage of 1 plus a half plus 1, which came to 2.5. So we tend to, in problems, have to eventually combine all the resistors. All resistors can be combined into one equivalent resistance. Remember, in our first circuit, the equivalent resistance was 2.5, and in our second open circuit, with the switch open, it came to 3 ohms. So that's what we mean by one equivalent resistance. Resistors in series are voltage dividers. Now, how do resistors in series divide the voltage? Resistors in series divide the voltage according to this proportion. The smaller the resistor in series, the smaller the drop in voltage. And we can use this formula. Voltage drop is resistance upon total resistance times total volts. Now, this formula is not in your data sheet, but it's such a useful one. I just want to go back to this here. So if we want to define the drop in voltage across this circuit, what we're going to say is we're going to say resistance 1 divided by total resistance. Now, it just depends. If we're talking about it when the switch is closed and there's double branches, the total resistance was 2.5. So it's 1 upon 2.5 times total volts, which is 1 volt. And that would give you the voltage drop across there. Okay, I'm just going to do it for you, just to show you. If I had to put in here a voltmeter in parallel, like that, and I wanted to work out the voltage here, I could use that formula, which is going to be, let's just use this text box. We could say, just want to move it to here. Voltage drop equals resistance divided by resistance total times, that's times V total. Okay, so let's put in an actual number. The voltage drop across P would be equal to, let's take, again, move this text box. So V across P is equal to, what was P's resistance? 1 divided by 2.5. And that answer, I guess I should have put it in brackets. Otherwise, it's going to times the total voltage, which was 1. So the voltage drop across P, when we had this circuit with 2 streams, is 1. That's the resistance of P over the total resistance times the total voltage. And let's just work that out. It's going to be 1 divided by 2.5 is 0.4. And so that is going to be, the voltage drop is going to be equal to 0.4 volts. That all adds up to 0.4 volts. Okay, so 0.4 drops there, 0.4 drops there, that's 0.8, and then 0.2 will drop across both of those. And that will add up to your 1. So that is how resistors in series are voltage dividers. And we can work out the proportion that each resistor drops. So that is 1 ohm over the total resistance, 2.5, times the total voltage, which was 1. And then, so that would be 0.4 because that's the same, also 1 ohm. That would also be 0.4. So 0.4 plus 0.4 is 0.8. So the remaining voltage will add up to 0.2. And so 0.4 plus 0.4 plus 0.2 adds up to 1 volt. Remember, for the amount that the voltage rises, it's got to end up back at 0. So it's got to drop by the same amount. So it drops 0.4, drops 0.2, drops 0.24 and gets back to 0 volts. Okay, so that's how that rule applies. So then here's our rule. In series means there is only one stream for the current, and the current flows sequentially through each component. Now, in parallel means there's a split in the conductor, and the current has a choice in which path its charge can flow. Resistors in parallel are current dividers. Let's just have a look at this circuit. Do you see how the current, which was, we worked it out, was 0.4 amps? This will divide the current. Doesn't have to divide it equally, but it will divide 0.4 into, in this case, because those are equal, into equal amounts, 0.2 and 0.2 amps. So the current divides. Resistors in parallel are current dividers. Resistors in series, that's that one, and those two combined, divide the voltage into 0.4 volts, 0.2 volts, 0.4 volts. Okay, getting back to our rules. Yeah, these rules are very important. You must learn them, yeah? So the total current is divided by resistors in parallel. Normally, when one sees resistors in parallel, one finds the equivalent resistor. Like when we wanted to do that problem, we had to work out what the combined resistance of the two resistors in parallel was. When given two circuits to compare, that's what we just did. Just make all components have one value, say 1 volt, 1 ohm, 1 whatever, and then work it out from there. That's an important point. When offered a choice, the most current chooses the path of least resistance. Remember, we said that. For resistors in parallel, the R total is less than the smallest resistor. So if you've got two resistors in parallel of 1, your resistance in total has got to be smaller than 1. If you have a resistor of, say, 3 and 4, the resistance for the parallel resistance is going to be less than the smallest one. So the combined resistance is less than 3. Please remember that rule. Resistors in parallel divide the current according to this rule. The greater the resistance, the smaller the current in parallel. Remember, resistors in parallel will resist the current, and the bigger resistance will resist the current more. Therefore, the current will choose the path of least resistance, and most current will go through the smaller resistor. If there is R, resistors of resistance X and 2X, if there are resistors of resistance X and 2X in parallel, then the current is Y and Y divided by 2 respectively. Okay, so suppose you have resistance X and the current is Y, and then you have a resistance of double, you're going to get half the current. Double the resistor in parallel, half the current. Why? The bigger the resistance, the smaller the current. And that's the rule you can use. If the circuit has an open switch, then that is an open circuit. And generally, you can ignore that part of the circuit as if it does not exist. That's what we did in that previous problem. If you are given a circuit with identical resistors, remember our problem had it, then make them 1 ohm and use Ohm's law to solve. Ohm's law is solved for total circuits and particular components. Use V total, I total, R total for the whole circuit. If we go to here, that's what I used. I total equals V total upon R total. we worked it out for the whole circuit, but I can also work it out for just one component. I could work it out like, say, remember we worked out the voltage drop here. Let's just apply Ohm's law just to this particular one. Okay, so what is Ohm's law? And let's say we're going to work out the voltage. So here's a text box. I'm just going to work out Ohm's law. So let's work out the voltage drop across T. I know the answer is going to be 0.4, but let's use Ohm's law to figure that out. So we say V equals volts equals amps times resistance equals, okay, what was the amps in this case? It was equals 2, sorry, the amps was 0.4. There we worked it out, equals 0.4 times 1, and that is going to be equal to 0.4 volts. So here we applied Ohm's law just to this resistance. So it's V specific equals I specific over R of the component. V of the component is amps of the flowing through the component, resistance of the component. And what was the amps through this? Remember, we'd work it out 0.4. So it was 0.4 times 1. This had a resistance 1, 0.4 volts. So here we used Ohm's law to figure this was 0.4. Here we used this formula to work out that it was 0.4. And we knew that the drop in voltage across that and that must be the same because they're identical resistors and they're in series. So to get back to our rules, so you can solve for particular components or for the whole circuit. You will always be given 2 of volts, amps, and resistance, and you will use Ohm's law to find the missing one. And this is really the secret to 90% of matric problems. They will give you, in a hidden way, 2 of those, volts and amps and resistance, or resistance and volts, and you've got to find the third or missing one. Now, just for general knowledge, our mains current that comes out of your wall plugs is 220 volts. It's AC, alternating current, and it comes out and it vibrates at 50 hertz. It alternates current at 50 hertz. Your current goes left, then right, then left and right. It reverses direction 50 times a second. Our electricity cost is about 2 Rand per amp hour or per unit. That means we can run an amp for an hour and pay 2 Rand for it. Power is equal to volts times amps, and it's measured in watts. Normally, our kettle's like 2,000 watts or something. A battery's capacity is measured in amp hours. So if you buy a battery, the bigger the amp hours, the longer it'll last. 1 amp for an hour is 1 amp hour. The most powerful appliances have the least resistance and the most current that most people don't know. If you buy a chainsaw and it's 3,000 watts, it's going to actually, that motor is going to have the least resistance. And that's why you get such a huge current. Huge current means you've got to pay a lot for it. Use a lot of amp hours. A short circuit is a closed circuit with no resistance and infinite current. Okay. And then fuses, so if you don't have any resistance in the circuit, you just close the positive and the negative side of the battery with a wire, the wire is going to get hot. It's going to get, we call that a short circuit. Fuses are there to melt when a short circuit occurs. So you put a fuse in, it's a piece of lead, and when it gets hot, it melts, and then it stops the short circuit. Okay, so those are the laws. There's probably more that we're going to have to think of. And with those laws, you should be able to solve all your electricity problems. I just want to do one more problem, and then I'm going to call this quits. Okay, let's find the next electricity problem here. Okay, here's a circuit. So here we got 2 identical circuits. Circuit 1 shows 2 identical lamps, X and Y. So they're again identical lamps. They've got that symbol. Connected to a cell of negligible internal resistance. The cell has got no resistance. Switch S is closed. So that's closed and that's closed. A wire T of negligible resistance is now connected across X as shown in the circuit. Which one of the following states would best describe how the brightness of the lamps have changed after T has been connected? There's a lot you actually need to know here. you need to know, for example, that the brightness of the lamps is the power of the lamps, and it's going to be power. Whoops. Let's just write that. Power equals volts times amps. And that is going to determine the brightness of your lamp. So it depends on two things, the current and the voltage. Now look what happens here. If you put a wire there, that's the path of least resistance. So all of your current is now going to bypass this bulb. That bulb is going to go out. And here you had two resistors in series. So let's suppose we said this has got a resistance of 1, that's got a resistance of 1, and then that's still got a resistance of 1, and that's got a resistance of 1 ohm. But this one doesn't count anymore because the current is going to go like this, in series through that 1 ohm, skip that. So the total resistance of this circuit is now 1 ohm, whereas the total resistance of that circuit was 2 ohms. So this circuit has got 2 ohms. This circuit has got a total of 1 ohm. So obviously, because there's less resistance, you're going to get more current through that bulb. And so if nothing else has changed, you're going to get more current through that bulb because this whole circuit got less resistance. Here's another thing that we could say. Here, the voltage is split. If we had to draw the voltage in a different color, there's 2 colors in the circuit. One there, then there would be a different color here. And let's just make it that color. And then there's a third color. We know that, in fact, this would drop it by, say this was a 1-volt battery. This would drop it by half. This would drop it by half. We could either use Ohm's law, or we could use resistance upon, which is 1, upon total resistance, which is 2, times total voltage. So 1 upon 2 is half a volt, will be drop across here. So here's the voltage is half a volt, but here there's only one appliance. So the voltage is going to go all the way there. It's going to be 1 volt, and on the other side, it's going to be 0 volts all the way. So this is going to drop it a whole 1 volt. Here, it's going to drop it half a volt. So 1 volt and twice the current, half a volt, and going to be less current because there's more resistance. And so our answer is going to be that Y is going to get brighter. So that's going to get brighter. It's one of those 2 answers. And X does not light up. Okay, so X does not light up and Y gets brighter. And so our answer is D. Because of that wire across here, X is not going to light up. And because there's less current, more voltage across Y, it's going to go brighter. Why? Because power equals volts times amps. You see, you've got to know all the rules. And with all the rules in mind, you should be able to easily do those problems. And I just want to, before I sign off, show you one last thing. Let's go here. Sometimes it's nice to play with circuits. And this actually was that very first circuit where we had a cell, then we had 1 resistor, then we had in parallel 2 resistors. We've got light bulbs, you can see. Then they come together, and then we've got 1 more light bulb. I think this was P, Q, R, and S, or whatever it was. That was that problem 1.38 or 9, I think. And look, it's also got a switch here, which we can open. And when we open that switch, this bulb stops glowing. And then we can close the switch again. Open it. Do you see how this gets dimmer? Watch the lines here. When this is open, there's more resistance because now we've got 3 bulbs in series. And so this gets dimmer. But this bulb gets brighter. More current now flows through this bulb and a greater voltage across this bulb. And so that one gets brighter and the others get dimmer. And so you can do this. You can play with this circuit called fet.colorado.edu. It's really nice to play with. And there was our one circuit that we talked about, our first circuit. And I just decided to make it here. Or you can delete everything. Then you can grab a battery. You can grab a wire, connect it. You can bend those around. You can add a resistor. So you just drag them to there. And then you could add a switch to this. And then you can add another. Let's just say we added another bulb just to see what happens. Let's just put the bulb there. And let's complete the circuit with a wire. So you first connect it on the end. Boom, like that. Then you move to there. Then you move it around and you'll see it'll join up. Then when we close the switch, a current flows. That's the electron flow. We can turn it to conventional current that flows from, you see this side's the positive. You can see there's a bump on the battery where it sticks out on the positive side. And when you open the circuit, nothing flows. You close the circuit, something flows. You could also do this. Just look how bright that is, okay? You can delete that component and then just move this to here. Now look how much brighter it is because we've reduced the resistance. And so you can play around with these circuits. Lovely to play with this. Then you can grab, say, a voltmeter, and you can put, say, the red on that side, and then you can say the black, move it to there. 0 volts. What about on that side? Oh, 9 volts. 9 volts. And you can play with, so where does the voltage drop? It drops across the resistance. Watch. On this side of the bulb, it's 0. On that side of the bulb, it's 9. So the voltage drop across the bulb has been 9 volts. Everywhere here is the same voltage. There's no voltage or potential difference. But then across the whole battery, so this is a 9-volt battery. So the 9 volts stays the same, still 9 volt, till it hits a resistance, which is your bulb, and then it drops to 0 volts. So the difference between this side and that side of the, let's just show you that. The difference in voltage between the two sides of the bulb are 9 volts. And so you can play around with that. Really super. Okay, so let's go back to our meeting. Let's stop presenting. Now, I'm sorry that we weren't able to get too many folks to come on board. I'm going to end recording now and put this video on YouTube, and then you'll be able to see it there, and I hope it'll help you with your electricity. So let's just stop recording.